going to talk about products and coproducts. These are another kind of universal property which pop up all over the place. They're a little bit more complicated than what we've seen before, which is terminal and initial objects. But actually, secretly, later on we'll find out that all universal properties are really just initial objects somewhere. But anyway, let's ignore that for now. Products are a way of encapsulating products. Well, anyway, here's a formalism which shows how products in various different places, such as products of sets, products of categories, products of groups, products of topological spaces, are all really part of the same story. So let's just go ahead and define products in a category. A product, given, so you take a pair of objects, given objects A and B in a category, a product of them, I suppose, product is given by the following thing. So you've got, here's the object that's going to be the product, but it's not just any old object. It's got to come equipped with some structure that tells us it's a product. And what is that structure? Well, it's a pair of maps which we consider to be projection maps, one going to A and one going to B. Now, of course, it's not just any old diagram like this. It's got to have a universal property. So what's the universal property here? It's a universal property saying, given any other diagram, so you take this diagram which has this kind of upside down V shape, and you say, given any other diagram with an upside down V shape like that, so it's got to have a pair of maps like this, say with an F and a G like that, there exists a unique factorization H. Now, what does it mean to be a factorization? It means there's a morphism from here to here that makes the whole diagram commute. So this side, this triangle over here has to commute, and this diagram, this triangle over here has to commute. Now, you'll notice that it's a bit like the definition of a terminal or an initial object, in that we said something, with those ones we had to say there exists a unique morphism somewhere. And you'll see that whenever we have a universal property, it basically comes out as saying that there's a unique morphism somewhere making something commute. And that's what it is here. So now you have to read this as a dynamic definition, because what I've written on the board doesn't actually make any sense at the moment. But it's sort of, so it's given by a diagram like this, such that for all diagrams like this, there exists a unique factorization like that. So that's how you sort of dynamically read this diagram. Now let's see immediately what the key example is for this. So you might sit down and go, okay, what kind of products have you met before? Of course, there are Cartesian products of sets, and so you think to yourself, ooh, I hope that these really are Cartesian products of sets, because otherwise this whole definition is pretty stupid. So let's see if this gives us a definition of Cartesian products of sets. Okay, let's get rid of this. So let's think about Cartesian products of sets. So what's a Cartesian product? You can have A cross B, and it's given by the set of all ordered pairs A, B, such that A is in A and B is in B. So let's see if this is a valid thing to put as our product here. So we're trying to say, is that a product? Well, first of all, does it come equipped with maps to A and B that we could call projections? Well, yes, it does, because given any pair A, B here, we can very naturally send it to A, little a down here, and very naturally send it to little b over there. So A, B goes to little a here, and it goes to little b here. And you should feel good about this now, because these are really canonical. They're really canonical maps. You didn't have to do any clever thinking or anything to produce these things. It was the only possible thing that it could possibly have been, possibly. So now the thing is to say, given any other set, V, together with a function f and a function g, do we get a unique function going from V to the Cartesian product of A cross B, making this diagram commute? So let's think about what it would mean. We do a little thought experiment to work this out now. You take a little object a little baby object v in there, and you think about where it would come down here. Well, it would come down to f of v over here, right? And it would come down to g of v over here. Possibly I'm over-adorning this diagram at this point, but let's plow on and see what happens. So it would come down to f of v and g of v here. Now, if you sort of think your way backwards up this diagram, if v is going to go somewhere in AB, it's got to go to a pair, such that goes to f of v and goes to g of v. And what could it possibly be? Well, the only thing it could possibly be, therefore, is f of v, g of v. Because we know that down here you just go to the first entry, and down here you just go to the second entry. So the only possible thing that you could have coming down here, making it commute, is v goes to f of v, comma, g of v. Right, so if it were true, then that's what it would have to be, this morphism, this factorization. So we've kind of seen that it's unique already. And let's just check that this actually works. I mean, is that a valid element? Is this, I wonder if the colour will show up, is this thing here a valid element of the Cartesian product A cross B? Well, yes, it is, because it's a pair where the first element is in A, because f of v is in A, and the second element is in B, because g of v is in B. And so this exhibits A cross B, not just as a Cartesian product of sets, but as a categorical product with this universal property that actually defines it. Now, one of the things that's nice about this is that, look here, when we defined the Cartesian product of sets, the first time round we had to talk about the actual elements of the sets here. And one of the things we like doing in category theory is taking constructions of sets where previously we had to talk about the elements of the sets and re-express them in such a way that we didn't actually refer to the elements of the sets at all. All we talk about here is the objects and morphisms of the category of sets. And once you've done that, you can transfer that language to other categories and see if you can get those same structures in other categories. And that's exactly what we've done here. We've got a definition of product that didn't have to refer to the individual elements of the individual sets. Now, you might be wondering, if you've been thinking about universal products or watching the videos about terminal and initial objects, you might be wondering if there's some kind of uniqueness property here. And remember, when we did terminal and initial objects, we saw that those weren't exactly unique in a category, but they were certainly unique up to unique isomorphism. And this is also going to be true here. Now, you can already probably guess, maybe, perhaps, possibly, that this Cartesian product has this property, but it's not the only way you could get something having this property. Here's a really stupid other way you could get something with a universal property. B cross A. B cross A is so not very different from A cross B that we probably don't even think about it ever. But it's actually different, because look, it's pairs BA. So now we've got the first element being in B and the second element being in A. And strictly speaking, this is in fact a different set from that set. But, of course, this is also a product of A and B. And so we don't want to say that products are unique. However, there is an isomorphism between these two sets, obviously, switching the two components over. And it's not just any old isomorphism. It's a completely canonical isomorphism that couldn't be, it's basically content-free. It's just saying, well, it's not saying anything, really. And so that kind of is telling us that we've got uniqueness up to unique isomorphism. And next time what we'll do is we'll see exactly what that means, because you do have to be a little bit careful about exactly what it means. Well, last time we defined categorical products and saw that they were, that Cartesian products were an example of categorical products. And for that reason, or for reasons like that, we usually write categorical products as products. But we have to be a bit careful about this, because it's one of those categorical moments where we write A cross B, but this isn't completely uniquely defined. And I started mentioning this at the end of last time. Whereas A cross B as a Cartesian product is uniquely defined as that actual set of ordered pairs, A cross B as a categorical product is just kind of any product. But they're all canonically isomorphic to each other, which is why we don't really worry about it. So what does canonically isomorphic mean? Well, you might think it means that given any other product, there's a canonical isomorphism with that one. Well, you have to be a little bit careful about that, because actually you need the entire diagram to commute. So the point is that supposing that we have a product equipped with its projection maps, and supposing we have another product, and I don't really know how to write it now, but supposing this is another product, it also has to come equipped with projection maps. And the point is that there has to be a unique isomorphism between those two products that actually makes the entire diagram commute. And this is a very important thing to remember when you're doing limits and co-limits, that it's not just the object that you're interested in, it's the entire diagram that exhibits this thing as the limit that you're thinking about. And one example you can think about to perhaps make this clearer is if you think about taking the Cartesian product of the set containing the elements 1 and 2 and the set containing the elements 3 and 4. Then the Cartesian product is a set of pairs 1, 3, 1, 4, 2, 3, 2, 4. Now that's just a 4-element set, right? So that's isomorphic to every other 4-element set that there is. But that doesn't make every 4-element set just like that into a product. Because to make it into a product, we have to decide what we're going to regard the projection maps as being. And when we've done that, essentially what we've done is we've decided which of our 4 elements is secretly going to be acting as these things. So for example, we could just say X, Y, orange, monkey. That's a perfectly good, albeit rather stupid, 4-element set. And this is isomorphic to that one. And you could express that as the product of these two sets. As it sits there now, it doesn't look an awful lot like a product of those two sets. But if we equipped it with these projection maps, then it would become a product of these two sets. And what we really have done would be to have kind of matched up these and say, well, secretly X is just going to be a rather odd name we've given to 1, 3. Y is going to be a rather odd name that we've given to 1, 4, and so on. Once we've done that, we would get a unique isomorphism between this set and this set. Because, of course, before we've done that, the isomorphism between these two isn't unique. And that's why the uniqueness of the isomorphism between these two things is so important. So the thing to take away from that load of wobble is that these things are unique up to unique isomorphism. They're not unique, and they're not just unique up to isomorphism. That's not enough. They have to be unique up to unique isomorphism. Right, so now let's have a look at a few more examples of products to try and just see how these things arise in various different categories. So we've already seen that they're Cartesian products in set. In the category of topological spaces, you also get products. You take how do you take the product of two topological spaces? Well, you take the Cartesian product of the underlying sets, and then you equip it with the product topology. So I don't know what to write now. You get the product topology. So another place you can take products is in the category of groups, where you can take the Cartesian product of two groups. And that's absolutely fine. Another place you can take them, well, if you restrict to abelian groups, it's still the Cartesian product, but in a slight fit of confusing terminology, that sometimes also gets known as the direct sum. Now, in general, sums are going to be dual to products, and when we do coproducts in a little bit, we'll see that that's exactly the dual notion to a categorical product. The reason this is also called the direct sum is because, in fact, it's a product and a coproduct in abelian groups, because abelian groups are so very special. And vector spaces, because they're based on abelian groups, have the same thing. So you can take the Cartesian product, and that's also the same as the direct sum, and that's the categorical product. Another place you can take products is in the category of categories, where you take the Cartesian product of your objects, and then you do the similar kind of thing on morphisms as well. So here the objects are pairs A, B, where A is in A and B is in B, and then morphisms, a morphism from A, B to A prime, B prime is going to be a pair of morphisms FG, where F goes from A to A prime and G goes from B to B primed. Another quite interesting place you can take products is inside any poset. So I'm not going to take products of posets at this point, but remember that if X is a poset, you can regard it as a category by putting a morphism from X to Y every time X is less than Y. So you encode the ordering as X less than Y. Now if we start off with this being a totally ordered set, then, so in a totally ordered set, if it's a totally ordered set, then the product under these circumstances, well, what's it going to be? We've got our X and we've got our Y, and what we want is some element which is less than X and less than Y, but sort of the best possible one. So without thinking about this too precisely at the moment, what's the best possible element that's less than both X and Y in an ordered set? Well, you'd hope it's going to be the minimum, and indeed it is. If it's a partially ordered set, what's the best possible element that's less than both X and Y? Well, if you sort of dream a little bit, what's the best one out of all the elements less than X and Y? What's the best one? Well, it's the biggest one, isn't it? So that's going to be the greatest lower bound, otherwise known as the inf, or the, am I going to get this right? It's this one, so it's going to be like intersection, which is the meet. So that's what this is. So in a poset, X cross Y is going to be X meet Y. And you can think about this like, if you think about the universal property, you want some object here with projection maps. What do projection maps mean? That means this object is less than X and less than Y, such that given any other element which is less than X and less than Y, there is a unique morphism here, which means that given any other element that's less than both X and Y, this element V has to be less than the one that we first thought of. And that corresponds to it being not just any lower bound, but the greatest lower bound. Right, what else can we think about? Oh yes, it's important to remember, here's an important non-example, that in general tensor products are not products, which is kind of why we call them tensor products, not Cartesian products. So for example, tensor products of vector spaces are not categorical products. However, the other way around it is true. So products in a category always give you a kind of tensor product, where by a kind of tensor product I mean something that gives you a monoidal category structure. So this is jumping ahead of ourselves perhaps a little bit, but if you have products in a category, that always gives you a monoidal category structure on there. And next time we'll talk about the dual notion, which is coproducts. Now we're going to talk about coproducts, which are the dual of products. What does the dual mean? It means that you're doing the entire same thing in the opposite category. And because we've done products already, we understand completely, that means that we already understand coproducts, so there's nothing left to say. Oh, all right, I'll say something. We're going to turn around this definition of a product. Remember that a product of A and B is an object equipped with projection maps like this, such that, here's the universal property, such that given any object equipped with morphisms like that, there's a unique factorization. So now, to take the dual of this, we're literally going to turn around every arrow in this diagram. Okay, off we go. So, let's turn them around like this. So that's the definition of a coproduct. It's an object U. This is still going to be the universal one down here. U is for universal. So it's an object U equipped with maps P and Q going into it, such that given any other diagram of the same shape, that is an object V equipped with maps going into it, there is a unique factorization, and that has to change direction as well. So now the unique factorization goes from U to V. A little point of terminology, When these were projection maps for the product, we called them projection maps. Should I try that sentence again? For the product, they went this way round, and we called them projection maps because of the analogy with Cartesian products, because they projected onto the first component and onto the second component. Now they're going this way round, we're going to see that they're insertion maps, because they insert A into the coproduct, and this one inserts B into the coproduct. So let's immediately have a look at sets, because those are the things that perhaps we understand the best. And you might think to yourself, I wonder what these are in sets. So I hope that you might have guessed by now or worked it out, because we're all very clever around here. And that is that they're going to be disjoint unions. So let's just have a little look at how disjoint union is a coproduct in set. So first of all, we certainly do have canonical insertion maps. A sits inside the disjoint union of A and B in a completely canonical way, and B sits inside the disjoint union of A and B. That's why they're called insertion maps. Each element here just goes to the copy of itself in the disjoint union. Now, supposing we had another set and maps like that, well, could we construct a map like this, and if so, would it be unique? So if we've got an F here and a G here, we do the same thought experiment that we did on the products, which is that we've got to think about where everything would go here, given that we know A has to go to F of A and B has to go to G of B in there. So how do we define, if we just think about ordinary disjoint unions, how do we define a function from the disjoint union to somewhere else? Well, we just have to decide where everything in A goes and where everything in B goes. Now, where could everything in A possibly go? If we take a little A in here, where's it going to go? Well, if it was an A starting from down here, then we know that it would have to go to F of A, right? And now this little A down here just gets mapped into its copy of itself in here. So this little A simply has to go to F of A. It's the only place it can go. And what about if it were a B? Because everything in here is either in A or in B, just one or the other, right? So if it was a little B, where would this little B go from down here? Well, it would just go to G of B, because that's what G does. So we know that this little B gets inserted into here and just hits its own image of itself. And so this little B just has to go to G of B up there. And so we can define a map on the disjoint union to be on the elements of A, it goes to F of A, and on the elements of B, it goes to G of B. That's the only possible thing it could have been. It makes everything commute, it's unique, that shows that this is a coproduct of A and B. Now, we can do all the same things that we did with products. We've got uniqueness up to unique isomorphism, just as before, and remember it means that if we've got another coproduct, there's got to be a unique isomorphism between them, making the entire diagram commute. What else is true? We've got the same issue that B disjoint union A is another coproduct, so we can switch those round. And we've got a whole load of examples in all the places that we just had before. So let's talk about those. Shall I leave that there? Shall I leave that there? Nah. Okay, so what have we got? In the category of topological spaces, we've just got disjoint union. In the category of groups, we have, given A and B, we've got the free product, A star B. And it is, I think you'll agree, slightly frustrating that this is called a kind of product, even though it's a kind of coproduct. But oh well, you think of it as a sort of disjoint union. It's the best you can do as a disjoint union, because of course if you take the disjoint union of two groups, then it won't necessarily be a group, because if you just shove the elements together, you won't actually have be able to multiply an element from this thing with an element from this thing. So then you have to generate something freely like mad, and that's what gives you the free product. So when you're trying to work out what a coproduct is, you can often try and take a disjoint union and then do the closest thing possible to taking a disjoint union if the disjoint union failed. Right, so we've also got abelian groups and vector spaces, and here it's direct sum. which, as we saw before, was also the product. It's, again, you can think of it, it's almost a bit more obvious that this is a coproduct, I think, than a product. That's my personal opinion anyway. Because how you take the direct sum of vector spaces, you kind of take the disjoint union of them, and then you go, oh dear, I need to be able to add them all together with each other if you take this one and stick them together. So again, you're taking the disjoint union, and then you're doing everything necessary to make it actually into an object of your vector, an object of this category. What else did we have? Oh yes, we had if X is a poset. Last time we had that products were greatest lower bounds, INFs, and it shouldn't come as any surprise to you that now we've taken the dual concept, we've got everything the other way around. So in a poset, X is a poset in, my grammar's gone completely up the spout, in X, comma, a poset, oh I don't know, a disjoint union, no, coproduct is, well this time it's going to be soup, that is least upper bound, otherwise known as this way around, which is called join. So again, I've got time to say this, no probably not, but never mind. You've got to think about it being, we've got maps going in this direction now, so the coproduct is going to be some object that's bigger than X and Y, and it's going to be the best possible bigger one. So it's not going to be a very, very bigger one, it's going to be the closest bigger one that you've got, so that's the least bigger one, that is the least upper bound. What was I going to say? Oh yeah, a quite interesting example is if you take base topological spaces rather than just spaces, then what you get is the wedge. So remember that a wedge is, say, if you take a space with a base point and you wedge it to another space with a base point, you kind of take the disjoint union except that these two base points have to get identified with each other. So you stick them together on their base point. So again, what you're doing here is you're taking the disjoint union, but then you're fiddling around with it to rectify the fact that you haven't got what you wanted. So if you just take the disjoint union of two base spaces, then you have an issue because now you've got two base points. So you correct this issue by identifying the two base points, and that's what the coproduct is in this case. So the moral of that story is that the universal property is telling you that you're somehow the best among all things, which might mean the biggest or the smallest or somehow canonical. It's the obvious one. It's the one where you don't have to make any choices because it's the biggest. And we'll see eventually that all universal properties can be thought of like that. Here are a few pertinent facts about products, mostly to do with morphisms. Now, we've seen already that the entire point of product is that you've got your projection maps A and B to A and B, which give you the fact that given any morphism F from B to A and G from B to B, you get a unique map like this. And once we've seen how that works with Cartesian products, this is just a piece of notation really. We usually call that F, comma, G, because in Cartesian products, you do F, comma, G on some object V, and what you do is you shove V into each of these components. So you get F of V, G of V. So this is in set. That's what you get. Now, one key example of this is the special case where you take A and A. So you take the product of A with itself, and then you use the identity maps from A to itself. And this is a perfectly good example of something that needs a unique factorization. Right? So you get a unique factorization here, which is a map from A to A cross A. And we usually call this the diagonal map, because if you think about what it does in set, then it's going to send A in set, it's going to send A to A, comma A, because it's going to send it to F of A, G of A, but F is the identity and G is also the identity, so it's just A, comma A. And this is often a very important part of product structures and something that we use a lot when we're doing products. Another important thing to remember is that you can do this in a slightly different way. So if you had a map from X to A, called F, and a map from Y to B, called G, then you could take the product here and the product here. So you take the product of X and Y, that gives you this, and you take the product of A and B, and that gives you this. And now look, if you look at X cross Y going all the way down to A and B like this, that actually is a diagram. This is the V up here, and then we've got the morphisms going all the way down the sides. So this is going to produce for us a unique factorization, which is a map from the product to the product, which also came from F and G, but in a slightly different way. And so we call this F cross G often to distinguish it from F comma G. And if you think about what it does in sets, the point is that you have F cross G, but what it's going to act on is something that was already in the product. So this acts on something which is already a pair, X comma Y, and you do it pointwise. So F then acts on the first bit, and G acts on the second bit, and that gives you the ordered pair in A cross B. You can relate this situation to this situation, because in fact what you're doing in the first case is that you could have, here what we could have done was this example using V over here and V over here as well. So what we get in that case is a map F cross G from V cross V to A cross B, and if we then compose it with the diagonal, we actually get F comma G, the F comma G that we originally thought of the first time round. So it can get a little bit confusing with the difference between this situation and this situation, so I just thought that I'd mention that for a second. The one other pertinent fact I wanted to mention about products, because it's quite useful for the future if you think about monoidal categories, is what happens if you take the product with something and the terminal object, if you have a terminal object. So what should we do? Let's just get rid of everything. Now I said before that if you have, you've got all products, then you get a monoidal structure, and that was a little bit, it was a little bit hand-wavy what I said there, because I haven't really said what it means to have all products. But one of the things that we'll need if we have a monoidal structure is a unit. And what I'm going to show here is the sense in which your terminal object, if you've got one, will give you something looking unit-like. So the point is, what happens if you take the product of some object with the terminal object? Now, I'm going to claim that this sort of acts in a unit-like sort of way, because what this is going to give us is something that's the same as what we started with. Now, how can we think about that? Well, all I'm going to do is exhibit A as a product of A and 1. And because of uniqueness up to unique isomorphism, that's really all this is saying, right? All I'm saying is that if you take a product A and 1, the thing you originally started with is a perfectly good one. So how do we prove this? Well, the first thing we've got to do is we've got to show that we've got projection maps, because remember, a product isn't just an object, it's an object equipped with projection maps going down the side. That's really important. So what could these projection maps possibly be? Well, let's have a look at it. Can we think of some canonical morphism from A to A? I can think of one. It's the identity. That's a pretty canonical kind of morphism from A to A. Now, what about a canonical morphism from A to the terminal object? Well, I can think of one of those as well. In fact, there is only one. The entire point of the terminal object is that there is a unique morphism from every object to it. So we've got some very canonical feeling morphisms like that. And you should start feeling like if your morphisms you've got are really canonical feeling, then they ought to have some kind of universal property about them. So what's the universal property supposed to be? We're supposed to say, given any other object and maps like this, there's some unique factorization. So can we do that? Now let's just have a quick think about what these two morphisms would be. This one is some morphism F, but this one is a morphism from V to the terminal object. And guess what? There's only one of them, because this is the terminal object. So this bit over here doesn't actually give us any information. So all we've got here is a map from B to A. And what we have to produce is a unique map here, making everything commute. Well, duh, what could it possibly be? Well, could it possibly be F, for example? Does that make everything commute? Jolly well ought to. Let's have a look at the left-hand side. That's the identity. Oh yes, that's just F. And what's that on the right-hand side? Well, does this commute? It has to commute, because this morphism ends at terminal object, and this morphism also ends at terminal object. They both start at V. So we've got two morphisms from V to the terminal object. So they've got to be the same morphism, because terminal objects, that means there's only one morphism from here to the terminal object. And in general, if you have some kind of crazy commutative diagram, if it ends in the terminal object, then all the maps from here down to there, no matter how you go through your diagram, will have to be the same. So that's something always useful for them to notice. If you're terminal there, then your entire diagram simply has to commute. So that is a use of terminal objects here, showing that if you take the product of A and a terminal object, you get yourself back again and nothing happens. That, I think, is all I wanted to say about that.